So now let's understand how to compute confidence intervals if I know the underlying distribution. Okay, I'll take an example. Imagine if I have a random variable x and let's assume it follows a Gaussian distribution. Again, Gaussian is our favorite distribution, but it could follow any distribution. But I'm just picking up Gaussian because it's easy for us to understand. Imagine that x is again the heights of folks, the heights of people. Okay, let's assume it follows a Gaussian distribution with the population mean equals to 168 centimeters and the population standard deviation equals to 5 centimeters. Let this be the case. I'm not saying this is what humans have. This is not the human population's mean and standard deviation. Let it be. I'm just making an assumption here. Now, as soon as you tell me that it's Gaussian distribution, I can make one quick observation or I can make one quick plot about it. Okay, so what it means is, right, this is my random variable x, right? The mean is here. Okay, the mean equals to 168 centimeters, right? This is my one standard deviation away, which is mu minus sigma. This is my two standard deviations away. This is my, again, this value is mu plus sigma, and this is mu plus 2 sigma, right? And so on and so forth, right? Of course, my mu is 168, and similarly, this value will be 168 minus 5, which is 163 centimeters, and this is 158 centimeters. Similarly, this value is 173 centimeters, and this is 178 centimeters, right? I know this is the PDF. This is basically the PDF of my random variable x. Now, imagine if I ask a question, if I say, if I want to give a confidence interval, if I want to compute the confidence interval of heights, okay? So can I say, so let's try to make a statement. I think that's a much better way of understanding this than just using some mathematical terminology. Since I know that my distribution follows Gaussian, okay, that's the first thing, okay? This is the first thing that I know. The second thing I know is, for a Gaussian distribution, 95% of the data lies between one standard deviation, lies between mu minus 2 sigma and mu plus 2 sigma. I know that 95% of my data, 95% of my observations lie in this interval. So if I compute what is mu minus 2 sigma and mu plus 2 sigma, I can say my mu minus 2 sigma is nothing but 158, which I just got it from here, and mu plus 2 sigma is 178, right? So I can say that the heights of people lies between 158 and 178 centimeters with 95% chance or 95% probability. Okay, this sounds very much like a confidence interval statement, right? Here I'm saying that the heights of people will lie between 158 and 178 centimeters with 95% probability. How did I come with this 95% value? Because I know for Gaussian distribution, I know it almost by heart now, okay, that mu minus 2 sigma and mu plus 6 sigma, this whole region which is highlighted here is 95%. I know that this region after the blue line, right, this region, so let me color this for you. This region is 2.5%, and similarly this region here is 2.5% in terms of volume of data. So you'll find only 2.5% of values which are greater than mu plus 2 sigma, and you'll find only 2.5% of values which are less than mu minus 2 sigma, right? And between these two range, you'll find 95% of values. So what we call this 95% value is called the confidence. It's often represented with a capital C. Okay, it's often represented with a capital C. Now, the important thing is your 95 is your C, because imagine if I ask you a question that I want the confidence interval of heights with 95% probability. Then your C is 95. So you'll try and find the central 95% values. And that you know almost by heart, because you know for Gaussian distribution, mu minus 2 sigma and mu plus 2 sigma, between these two values, there is 95% of volume, or 95% of observations will fall in this region. You know that almost by heart now, right? So let me draw the Gaussian distribution again carefully so that I can explain a simple concept much more clearly. Okay, so this is my mu. Okay, let's assume this is my mu minus 2 sigma and this is my mu plus 2 sigma. Okay. Okay. So let's see. So if I highlight this whole region, right? In this whole region, I call this region C, which is 95%, right? This region here, this blue region here is 2.5%, and this blue region here is 2.5%, right? Now, since I know that it's a Gaussian distribution, if somebody asks me, if somebody says, can you give me the confidence interval? Can you give me the confidence interval with, let's say 90%? If somebody asks me, can you give me the value with for 90%? Okay, how do I come up with these values now? Or if somebody says, give me the value for 80% or 70%, I basically choose the central region here. It will no more be mu minus 2 sigma and mu plus 2 sigma. It will be some other value here. Okay, I'll find the appropriate values here. So this region is C. If this region is C, this region is 1 minus C by 2. And this region here is 1 minus C by 2. Right? C is 95%, which means C is 0.95. Right? 1 minus C by 2 is 1 minus 0.95. 1 minus 0.95, sorry, by 2, sorry, by 2, which is equal to your 2.5%, and this is also equal to 2.5%. So when somebody asks you about 90%, 80%, and 70%, what do? You basically do this. You basically say, I know that my data comes from Gaussian distribution. I know that this is the mean. I want to find a region. I want to find the bounds such that within this region, I have 90% of my points. Okay, my C is 90%. Suppose if somebody says, give me the values of the lower value and the upper value for heights with 90% confidence, or with 90% confidence, then what do? You basically say that this value is 90%. So what should this value be? Let me just highlight this. What should this value be now? It is 1 minus C by 2, which is 1 minus 0.9 by 2, which is 5%. Similarly, this region also should be 5%, right? Now you say, at what value? What is this value? What is this value? What are these two values? Okay, let's call these values x dash and x double dash. Okay, now you have to ask yourself, what are these two values, right? Such that in between these two values, there is 90% of observations. Doing that, of course, to answer that question, you can basically use something called as normal distribution tables. Okay, actually all of this data is tabulated. In the olden days, in the pre-computer days, you got some tables called logarithmic tables and normal distribution tables. It's actually a small book that you would get with all these tables. You can look up in the table and you can find what the value of x dash and x double dash are. And you can now say that your heights lie in x in the interval x bar and x dash and x double dash with 90% confidence interval. Okay, so that's how you compute for any given confidence interval C. That's how you compute what is the lower bound. This is called the lower bound of the confidence interval, and this is the upper bound of the confidence interval. Now, the good thing is we often use 95% because we know how to compute for 95%, because I know from the properties of Gaussian distribution that between mu minus 2 sigma and mu plus 2 sigma, 95% of the values will lie. So this is mu minus 2 sigma and mu plus 2 sigma for 95%, right? This almost I know it by heart. Okay, and hence I don't have to worry. So you might wonder why people use the 95% confidence interval a lot. It's because it's easy to compute for a Gaussian distribution, right? 90% is harder because I don't remember it by heart. I'll have to go and look at normal distribution tables to find what the value of x dash and x dash and x double dash are. So this is one way where if you're given the distribution, again, remember in this case, I know that my x is distributed with a Gaussian distribution with mean mu and sigma. If I did not know this, I cannot do all of this. So you can compute a confidence interval if you already know the underlying distribution. If you already know the underlying distribution of your random variable, you can easily compute the 95% confidence interval. And we use Gaussian a lot. That's why I brought this topic up here. There are other distributions like t-distribution, which we will use, but confidence interval of Gaussian distributions. So for most of the case, we use 95% because Gaussian distribution, we know by heart. has 95% of the observations in mu minus 2 sigma and mu plus 2 sigma.